Okay, we are going to talk about capital budgeting uh, once again. This is part two of the lecture on capital budgeting. And what we'll do here is last time we actually looked at a project and, and cash flows for a project and figured out how to calculate the payback period, the discounted payback period, the NPV, the net present value, the IRR, internal rate of return, MIRR, modified internal rate of return, etc. And this time, and then individually, um, those various measures could tell us whether a project is acceptable or not. But when we have um, more than one project and we have to choose between the two, that's when we have some issues that could occur. So if we're just looking at a single project, we could make all our decisions based on NPVs, and it would be okay. We're talking about independent projects, but for mutually exclusive projects, NPV doesn't always do the job. Last time we saw that we could use something like a profitability index or a PI if we were subject to capital controls, um, but we're going to look at the different methods over here. Um, and so let's bring in another project, right? And look at the issues that come up with mutually exclusive projects. So it's the same company, Tit for Tat Corporation, also has the option of installing a cheaper pollution control equipment, and that's called Project S, which costs only $500,000. The expected after-tax benefits will be in the tune of $90 or $90,000 per year over the 10-year life of the equipment. Um, so this is actually easier to evaluate because the cash flows come in the form of annuity, 90,000 per year for 10 years, right? So what's the payback period? What's the what is the NPV of this project? What's the profitability index, IRR, MIRR for this project? Then we'll compare this project. Which project is better in economic sense at the current cost of capital? So this is Project S. The previous one was called Project X, and we'll have to figure out which is better. And then when does Project S become economically advantageous? So there's actually at certain times X will be better, at other times S may be better. So let's look at those. First, let's calculate the payback, NPV, PI, IRR, MIRR for this project S, right? So to calculate the payback period, we need to build the cumulative cash flow. And in this project, we just had a $500,000 investment, so negative 500,000 is the cash outflow right now. And then we get 90,000 and 90,000 each year for the next 10 years. So that makes it easier to evaluate, right? So of course, to get the cumulative cash flows, we start with the minus 500,000, we add 90,000, and we get minus 410,000. We add another 90,000 for year two, get 320,000, and so on. And we see that between 5 and 6 years, this project pays back. So it's 5 because that's when cash flows turn from negative to positive. So, but what part of the sixth year? Well, it's going to be based on the 50,000 that still remains to be recovered after 5 years as a proportion of what is recovered during year 6, which is 90,000. So it's 5 plus 50,000 over 90,000. Right? So it comes out to 5.6 years. So that's the payback period for Project S. Of course, to get the NPV, IRR, MIRR for this project, it's easy because what we have, let's see, for NPV and IRR, um, we can simply use the cash flow mode. So turn on the calculator. Second, if we and if I just said 90,000 is the payment, right, and then 10 is I by Y, and 10 is also N, it's 10-year project, and then I want to calculate the present value of this compute PV. We get, that's the present value of this project, right? Make that positive and then subtract the initial investment. So what we have is present value of all the future cash flows, and then we subtract the initial investment of 500,000, and we get the NPV. So that's the NPV, $53,011.04, right? So that is the NPV for this project. Of course, to get the profitability index, we can simply add back the initial investment of the 500,000 and divide the result, which is the present value of all future cash flows. We'll divide that by the initial investment, and we get the profitability index for this project, which is 1.106, right? To get the IRR, we can still just simply use this mode. So second FV, to clear this thing, we'll say 90,000 is the payment, then 500,000 negative is the present value, and 10 is N, and compute I, and we get 12.41% is the internal rate of return for this project. Okay, then to calculate the MIRR, second clear TVM, remember how MIRR is calculated? It's the future value of all the cash flows computed, all the positive cash flows, future value of all positive cash flows computed at the cost of capital. We need the present value of all negative cash flows computed at the cost of capital to get the MIRR. But once again, the only negative cash flow is the $500,000 investment, and it's already in present value form. So we don't have to worry about calculating present value of negative cash flows. But we do have to worry about calculating future value of all these positive cash flow, which were 10 in number, right? So 90,000 is payment, 10 is N, 10 is also I, compute FV, and we get the future value, right? So let's store this number, and then second FV to clear TVM. Then, well, actually, didn't need to store it because it stayed on the screen even after clearing it. Let's make it positive. That's the future value. Then the 500,000, the initial investment negative is present value. 10 is N, compute I, and we get 11.11%, and that is the MIRR for this project, right? So these couple of slides, that's what we're showing, all those calculations that we just did to calculate the IRR, NPV, IRR, MIRR, and profitability index. Okay, so for the two projects, including the one in the last lecture, Project X and then Project S. For the two projects, here's what we have calculated. The payback period for Project X is 5.5 years. For S, it's 5.6 years. And we want earlier payback, so X appears to be better. If we look at NPV, X has higher NPV than S. So we want higher NPV, so X looks better than S. But when we look at profitability index, of course, this is the benefit scaled for the size of the project. S has a higher profitability index, so that looks better. Same with IRR and MIRR, right? So we look at the first two criteria. Project X looks better than S. For the the last three, S looks better than X, right? So which one should we use, right? Which one of the two should we use? Well, and the answer here is going to depend on circumstances, right? We can certainly discard all the results we got from payback period and from the IRR, but even if we look at NPV and MIRR, we still have a conflict. At NPV and profitability index, we have a conflict, right? So it depends on if we have any capital constraints, then we will use the PI and use 1.106, right? If we don't have any constraint on the amount of capital that we can raise, then should we use NPV or MIRR? And the answer is basically NPV because it has it tells us the dollar amount of benefit that we can get from investing in this project. So we note that while both projects are individually acceptable, we get conflicting signals. We had to choose one, right? Also note that NPV, PI, MIRR, those are the three things that actually, so NPV, profitability index, and MIRR, those three things can change if the company's cost of capital will change, right? So we look at the NPV profiles of the two projects, X and S. This is what we get. Well, basically what an NPV profile is the NPV of a project at different costs of capital, right? So we're calculating present value of cash flows to get the NPV. And as the cost of capital increases, the NPV decreases, and we see a curve that has a negative slope. And with project X, if the cost of capital was 0, then you just simply add up the cash flows because present value, future values are all the same, and you will get a positive 700,000. And for project X, you'll get 400,000. Okay, because project X is have only had 90,000 cash flow for 10 years. That's 900,000, and subtract the initial investment of 500,000, then NPV would be 400,000 if the cost of capital is 0, right? But as the cost of capital rises, its NPV declines as well. IRR, by definition, is where NPV equals 0. So NPV equals 0, and we found out that internal rate of return, or IRR, for project X was 11.38%, and for S it was 12.41%, right? So if we are looking at IRR, we'd always pick S over X, right? Of course, we want to make sure that the IRR is greater than the cost of capital, but the cost of capital, if it's 6% or 8% or 10%, we'll pick this S over X, but not with NPV, because you can see that the two lines cross. And so there is a point after which the NPV of X, right, is better than NPV of S. But before that, NPV of Fs is higher than that of X. And that point is called a crossover point. And so we call it crossover point because prior to that, NPV of X is greater than that of S. After that point, NPV of S is greater than that of X, right? With IRR, nothing changes. IRR, and there's one IRR. These are both conventional projects. There's only one IRR for each of them. And, the preference will always be S over X. So we have conflict. When do we have conflict? We have conflict in this earlier region where the cost of capital is less than this crossover point. As a matter of fact, we calculated NPVs based on a 10% cost of capital, and that's why we found the conflict, where NPV was saying pick X over S, whereas IRR is saying pick S over X, right? And this, we can find out there's a way of calculating this crossover point, and we can find that it's 10.29%, right? So how do we find the crossover point? We simply have to build a table of differential cash flows, right? So take the cash flows of X and subtract S from it, or you could do S minus X. Either way will work, but let's do X minus S. And when we do that, of course, here's the difference in the cash flows, right? And then we can use the difference. So minus $1 million minus negative 500,000 is minus $1 million plus 500,000, right? That leaves us with negative 500,000. 150,000 minus 90,000 is 60,000. And so those were the cash flows for X. We subtract the cash flows for S for each year, and then we can find its IRR. So in the calculator, we're gonna, of course, we will use this, the cash flow mode now, right? Clear second C/C to clear the cash flow mode. C of 0 is 500,000 negative, right? Enter. C01, we got 2 years of 60,000, so it's going to be 60,000. Enter. Then frequency of that $60,000 cash flow is 2. Enter that. Then it's $110,000. Cash flow that repeats for 5 years, 1, 2, 3, 4, 5. So the frequency F02 is 5. Enter. And then we get $45,000 cash flow. 45. Enter that. And that repeats for 3 times. So frequency of that is 3. Okay. And once we have that, now we just need to calculate the IRR of this differential series of cash flows. So click on IRR, then hit compute, and then get the IRR, which is 10.29%. This is the crossover point. That is how we calculate this crossover point, 10.29%. Okay, so let's go to the next slide. And since the current cost of capital is less than the crossover rate, we find that project X has higher NPV, even though it has a lower IRR. What should we do? We should still pick project X. This is due to the faulty reinvestment rate assumption in the IRR criteria. when the cost of capital exceeds the crossover rate, NPV of project X becomes higher. As long as the NPV is still positive, we should put S over X, right? So it depends on what the cost of capital is. But we should, as long as we go with NPVs, will be fine. In this particular case, because both projects are conventional projects. Right? And they have the same life, and we don't have any capital constraints to worry about. All right, but let's look at the multiple IRR problem, right? If we have a project with unconventional cash flows for this, for instance, this one, Tit for Tat has an unconventional option in the form of Project FAT, which has cash flows of negative 60,000 at inception, 155,000 after 1 year, and minus 100,000 after 2 years. And the company's WACC remains 10%. What is the IRR for Project FAT? Discuss the problem that we might face in computing the IRR of this project, right? So if we were to calculate the IRR of this project using the cash flow mode, we would input 60,000 as negative 60,000 as CF0. For CO1, it's a positive 155,000. Enter that, right? And then negative 100,000. Frequency is just 1, but negative 100,000 is CO2. Okay, and if we want to calculate its IRR, then push IRR and hit compute. Let me see if it doesn't look right, so let me see if the cash flows are correct. Minus 60,000 plus 155. Oh, I guess I didn't push enter when I put this negative 100,000 for C02, enter. Okay, now let me recompute IRR. Well, we get 25% as the IRR, right? And if the cost of capital is 10%, then the IRR criteria says it's an acceptable project, right? So if I calculate NPV for this project at 10% IRR, right, I get minus 1,735, so a negative NPV, right? So certainly with the NPV criteria, we should not pick this project. So of course we get a conflict, but the reality is that for this project, if you were to calculate NPVs at different costs of capital, you will see that the profile, the NPV profile for this project actually crosses the x-axis twice when the NPV is 0. And remember how we define IRR? It's the rate at which NPV equals 0. Right? So this has an unconventional NPV profile. Instead of just one downward sloping curve, we've got a parabolic curve over here. And there were 2 sign changes, and you can get 2 IRRs. As a matter of fact, if you look at a series of cash flows for a project, and if it has multiple sign changes, we can have as multiple IRRs. In mathematically speaking, you can have, with 5 sign changes, you will have 5 IRRs. Now, some of them may be imaginary roots. You know, you're talking about roots of multinomial. So some of them may be imaginary roots, and some may be real roots. I'm talking about imaginary numbers in math. So you may not actually have real IRRs, 5 real IRRs with a project which has cash flows that change signs 5 times. But it's possible to have as many as 5 IRRs over there. Here we had a project which had a negative cash flow, then a positive, then another negative, right? So we have 2 times that the signs of the cash flow change. Once from negative to positive, another time from positive to negative. So we possibly can have 2 IRRs, and those are the 2 IRRs. And the calculator actually it has to guess and find the correct answer, right? That's what the algorithm does. It starts with the guess and closes it and on the answer through multiple guesses, So it will start at 0, or something very close to 0, and finds out that the NPV, finds out that that's not the correct answer, and then it starts to guess at some higher rate until it actually closes into the right answer, right? So what it does, it just calculates picks a rate, calculates the present value of all future cash flows, and that's not equal to the initial investment. Then it knows that's not the right answer, right? If it's higher than the initial investment, it'll pick a lower rate next. If it's lower, it'll pick a higher rate next. Anyways, so the algorithm for IRR does that guesswork in the calculator, and it started with 0 and closed in on the closest answer, which was 25%, right? In a spreadsheet or in some more advanced calculators, you can actually start a seed, say, calculators start guessing from this number, and then if you put in 50% as a seed, you will get it'll converge to 33.33%, right? Anyways, but the more important point is that we can have problems with IRRs and a multiple IRR problem, and of course we can't even use the IRR criteria, which said compare it to the cost of capital. Well, if IRR is 25%, cost of capital is 10%, the IRR criteria said, oh, that's a good project, accept it. But what happens here is that if the cost of capital is less than 25%, then we get negative NPVs, right? It's not really good. In this particular case, only the times when the NPV is positive is if the cost of capital is above 25% and less than 33.3%. Okay, so let's calculate the MIRR for this project, right? And once again, remember, to get the MIRR, we need to calculate the present value of all the negative cash flows, which we have 2 negative cash flows in this case, right? So second, I'm going to exit from here, second, quit, oops. Okay, we have 2 negative cash flows. The first one is already in its present value form, which is 60,000. The second one happens 2 years down the road for this project, and so if we calculate its present value, 100,000 is future value, 2 is N, and we're using the cost of capital, 10 is I by Y, compute PV, we get minus 82,644. Well, let's add to it a negative 60,000, which was year 0 cash flow already in its present value form. And we get, so negative 60,000 and negative 82,644 gives us negative 142,644. Now this is the present value of all negative cash flows. Store it. That's to get the present value of positive cash flows. There's only one, and that was in year 2, or sorry, year 1, 155,000. And we want to find out its value after 2 years. So we need to take it forward 1 year. So when 10 is I and 1 is N, and we need to calculate its future value. And we get 17500. Obviously, we need to make that positive, store 2. Then second, clear TBM. Well, that 170,500 is future value. This number we had stored, which was the present value of all negative cash flows. Recall 1 brings it back, make that present value. 2 is N, and then compute I by Y, and it comes out to 9.328, right? And that is the MIRR for this project, right? And now, if we use the MIRR criteria and compare it to the cost of capital, which is 10%, then we get the correct answer, right? So for an independent project, MIRR is just as good as NPV. But mutually exclusive projects, MIRR still may not work, right? As we saw between project X and S. Okay, now let's learn about handling a couple projects that do not have the same life, right? So we got 2 projects, Project Elephant and Project Badger. And Project Elephant is a 4-year project. Badger is a 2-year project, right? They both have the same capital outlay, $1 million, right? So the question is, which one of these projects should you select? And we cannot really answer this based on NPVs alone. We'll have to do a replacement chain or equivalent annual annuity, and let's see what those are. So if we calculate the NPV of both projects, we'll get 124,513, 96,694, and just quickly calculate the NPV for the 2 projects here. Go to the cash flow mode, second C/C. So $1 million is the initial investment. Project Elephant has $400,000 cash flow for the first 2 years. Enter 400,000 for the first 2 years. Happens 2 times, and then 300,000 for the next 2 years. CO2 is 300,000. Enter also twice, and then we need to calculate NPV at 10%. So that's the NPV of Project Elephant, 124,513, 35, right? For Project Badger, well, go back to cash flow, second C/C, 1 million negative as CF0, CO1 is 570,000. Enter that. Frequency is 1, CO2 is 700,000. Enter that, and then go to NPV and put 10 for I and compute, and we get 96,694.22, right? So those are the 2 NPVs. But we can't just go with NPV, right? It would appear that Project Elephant is preferable to Project Badger, but not so fast. Elephant ties up your $1 million investment for 2 years, while Badger only ties for, I'm sorry, Elephant ties it up for 4 years, Badger only ties it for 2 years, right? What is NPV? Well, the NPV is your $1 million investment recovered plus this much money in present value terms, right? But you get that investment back in 2 years with Project Badger. So you could probably pick another one of these and invest it in it for the next 2 years. So it may be feasible to invest in another Project Badger after 2 years. Well, if you do that, you can basically form a replacement chain. So this is Project Badger with replacement. We're going to invest $1 million and recover $570,000, and then $700,000 in year 2. But at the same time, we're going to invest in another Project Badger. So invest another $1 million. So your net cash flow is going to be negative $300,000 in year 2. And then just like Project Badger repeats, as repeating itself, paying you back $570,000 and $700,000, right? So for Project Badger with replacement, the NPV might look different, right? So we go back to the cash flows. Now we have Project Badger, which had CO1 of $570,000, but C02 is not $700,000, but rather negative $300,000. Let's enter that. And then CO3 is 570. Enter. And then CO4 is 700,000. Enter that. And then if we calculate the NPV at 10%, we get 606.79, right? So we do a replacement chain, we find that the NPV of Badger with replacement is actually higher than Elephant. So we should pick Badger. Well, it's not always easy to form a replacement chain, right? It was easy here because there's a 2-year project and a 4-year project. And so 2 easily divides into 4 twice, right? But projects with different lives will always have a problem. This problem, but forming replacement chains can be complicated. For example, think of a 5-year versus a 7-year project, right? There's no common, divisor, or basically you just have to multiply 7 with 5. They're both prime numbers. So you get 35 years. You'll have to repeat the 7-year project 5 times. You'll have to repeat the 5-year project 7 times. And you have to analyze both projects replaced, and it'll be a 35-year comparison, right? And then a more simpler method is to annuitize, right? So we take the benefits from each project and annualize it. So another solution is to annuitize the project benefits. In other words, we can take a project's NPV and spread it over the life of a project, thereby examining the benefits per annum, right? So to calculate the EAA, take the project's NPV and input that as present value in the calculator. So if we go back, and here were the original NPVs of the 2 projects, right? Second, quit. We need to get out of this mode. Then second FV, what we want to do is say this is a 4-year project, and this is the benefits from the 4-year project. Let's spread it over 4 years of the life. So 1, 2, 4, 5, 1, 3. We can't just divide it by 4, right? Because then we are ignoring time value of money. But you make it the present value of an annuity. So make it a present value of a 4-year annuity. 4 is N, and 10 is I by Y, and compute the payment on this 4-year annuity. Compute PMT, and you get 39,280.33, right? For Badger, you do the same thing or similar thing with Badger. Second FV, make 96,694. That's the NPV. 0.21, right? So that's the NPV of Badger. Make that the present value. Badger is a 2-year project. So 2 is N, and 10 is I by Y, and compute PMT. And you get 55,714.29. And that's the equivalent annual annuity for Project Badger. So here are the two answers that we just calculated. Elephant EAA for Elephant is 39,280. For Badger, it's 55,714. So once again, we find that Project Badger is a better project. Okay. All right. Now let's talk about how a company may actually determine its optimal capital budget. If it's looking at several projects to invest in, in the future, and how much money it should spend and what projects should it accept, right? We are saying that all of these projects are acceptable. They are independent, right? Except taking one doesn't preclude taking on another. So the company has to take care of financing these projects, has to raise funds, and its weighted average cost of capital, well, at first it's 10% up to $3 million. Remember, you raise more money, the cost of debt and even the cost of equity starts to go up. And so the weighted average cost of capital can start to go up as well. So after the first $3 million, the next $2 million, when it has to invest the next $2 million, it will cost 12%, right? And then after that, the cost of capital goes up to 15%, right? So what's the optimal capital budget for the company? Well, we need to prioritize. Let's go back and look at the projects themselves. The projects, this is how much you need to invest for each of these projects, and the MIRR is computed for each of the projects. And of course, we cannot take, suppose the cost of capital is at 10%, T is out, right? We cannot use T at all. You can't take on T. But we should order these projects based on the benefits or the MIRR we see. And we start with the highest MIRR, which is for project Y, then the next one, which is project D, and then the next one, Z, L, X, T. And so we've ordered these projects based on their modified internal rate of return. And now we can overlay, this gives us an investment opportunity set. That's why we're calling it investment opportunity set. So we can overlay this on the marginal cost of capital schedule. So the marginal cost of capital is 10% up to $3 million, right? Then it goes up to 12% for another $2 million, so up to $5 million. Then after that it is 15%, right? When we look at the different projects, Y has the highest benefit, and it's going to take $2 million. That was the amount that we needed to invest in Y, right? So we we have calculated the cumulative capital budget for, we start with Y, which needs 2 million, then D, 800,000, so cumulative capital budget is 2.8 million. Then Z takes another 500,000, so 3.3 million, and so on. And that gives us this investment opportunity schedule for, and we can see that after we have invested in Z, the other investments actually provide a lower MIRR than the marginal cost of capital. So that is 3.3 million as the optimal capital budget for this company over the next year. All right, so this is the end of capital budgeting lectures. We'll see you at another time with the different